So I'm going to tell you a little bit about our work in metamaterials and metasurfaces, in fact, to generate and manipulate terahertz radiation. So just to start out, the terahertz spectrum of radiation actually lies between, let me see if this works, uh, lies between the electronics world, which is radio, TV waves, microwaves, and the optical world of infrared and ultraviolet radiation. So 1 terahertz is about a picosecond in duration, 33 wave numbers, a wavelength of about a third of a millimeter, in energy space, 4.1 MeV, 48 Kelvin. We are focused on ultrafast terahertz radiation. So the diagnostic that we often use is called time domain terahertz spectroscopy. So terahertz, you wonder why people are interested. It has a number of applications, one of which you use at the airport in terms of, security screening, but non-destructive evaluation is a security application. There are also a number of applications, and I know this slide is a little bit fuzzy, but in industrial applications, which often include imaging, sometimes include spectroscopy, thickness measurements, and so on. In defense and security, which is mostly imaging, biomedical, a lot of imaging in areas like dermatology, dentistry, but also spectroscopy using terahertz radiation. And then high-speed communications, where you use the short pulse width, broadband communications, where you use the broad bandwidth of a terahertz pulse, and then other more somewhat scientific applications in astrophysics and atmospheric chemistry. So unfortunately, for those who want to use terahertz, there's kind of a gap in terms of both sources, which is shown here. There are good sources at low frequencies, good sources at optical and infrared frequencies, not so good in the terahertz regime, but also for the kinds of devices that you use to manipulate materials, optical and optoelectronic devices, because there aren't a lot of natural materials there. So a solution, which we've looked at a lot, is metasurfaces. So metasurfaces enable a variety of optical and terahertz functionalities that are hard to accomplish with natural materials. So I'm going to talk, the rest of the talk is going to be about metasurfaces and how we develop them and how we use them. So basically, metasurfaces are two-dimensional sub-wavelength resonator arrays. It's a surface, so there's basically an effective surface and an interface, and you design a resonance there. So you design dispersion and absorption. You can actually design, so there are phase continuities, gradients, and design the polarizability. What's nice about them is that you can assemble them using standard fabrication techniques. So you go into a clean room and you can make them. And especially in the terahertz regime, the dimensions that we're talking about, are on the order of 50 to 100 microns. So pretty easy in terms of fabrication. And because of that, they're amenable to functional integration into materials. These resonators are little metal antennas, which you can model as RLC circuits. Okay, so you can really develop an intuitive grasp of what metamaterials do or metasurfaces do. So one important aspect, in fact, the main aspect of a metasurface, is that you're really able to design it so that you've got a resonance at a specific frequency, in this case in the terahertz frequency, and you also can design the dispersion, the phase, and how the phase varies with frequency. And that enables you to tailor the amplitude and phase of the radiation and enables you to develop novel functionalities, especially in the terahertz regime. A second concept is what is known as multi-layer or few-layer metasurfaces. So in this case, you've got a metasurface at the front, air spacer interface. You've got a spacer, which is a dielectric and a gap. And you've got a second metasurface that's on the substrate. And by doing that, you not only are able to design the dispersion on each of these surfaces, but you're also able to use the constructive or destructive interference of these two waves at the two surfaces to enhance whatever functionality you're interested in. So this is one example of a bilayer metasurface that actually produces terahertz frequencies. And so design you design the metasurface for a specific resonance at a specific frequency, and then you tailor the distance of the or the thickness of the spacer, which is again a dielectric, mylar, or something else, depending on what you are doing, such that you get an optimal anti-reflection and an optimal transmission. So as you can see here, that lies somewhere just above 1.5 terahertz. You can also make these kind of broad or narrow band filters using a pillar structure, which is shown here. And as you vary the pillar diameter from 32 microns to 64 microns, you basically change the frequency of the resonance. Okay, so this is another way you can design a specific optical functionality using metasurfaces. You can you can try another, you can look at another kind of functionality, in this case, a metasurface perfect absorber. And so this is actually designed by putting the second metasurface is basically a ground plane, so you don't get any transmission. And then you design the first surface for the resonance at the appropriate frequency. And as you vary the spacer thickness, you can optimize the perfect absorption. So you get perfect absorption within this particular optical component. And this is again due to constructive and destructive interference, in this case, destructive interference. So you can also do things with polarization. And now you're getting into more complex optical or terahertz functionalities. So you can engineer the metasurface phase so that it has a constant phase difference over a specific bandwidth. Okay, in this case, about 0.6 to 1.3, 1.4 terahertz, but also has a high reflectivity over that range. If you look at both the reflection perpendicular to a metasurface and parallel to a metasurface. In this case, this is a 2 pi phase difference. So that would give you one functionality, but one that's, I think, of more interest and that we demonstrated is a polarization conversion from a broadband linear polarization to a circular polarization. So in this case, the terahertz wave would come in here at 45 degrees. You get both components. And there'd be a phase difference, which is basically pi over 2. And so that converts, and the reflectivity is close to unity for both of these reflections. So that basically gives you right-hand circularly polarized light over a specific broadband wavelength regime in the terahertz, and almost no left-hand polarization. So again, this is a optical component that's hard to develop using natural materials, but metasurfaces allows you to do this. Another interesting polarization control using metamaterials is this kind of a construction. So converting X polarized light to Y polarized light with reasonably high efficiency is shown here. So you can do it in reflection using, again, these wire strips with the appropriate spacer and a back plane. If you want to do it in transmission, it's actually a 3-layer device where the front and the back actually act as polarizers, basically. They transmit in one direction and reflect in another. So again, this demonstrates how you can convert one polarization to a second polarization with reasonably high efficiency. Okay, so one, I guess, final example is the development of what we call flat optics. And again, this is enabled by controlling the phase, using our little resonators to control the phase, and using the concept of a generalized Snell law, where basically the refractive beam depends on the derivative of the phase with respect to the one of the directions. So what we have here are a number of different resonators, each producing pi/4 phase shift. If you put 8 of them in a row, you get a 2 pi phase shift. And so you get a dφdx that actually gives you, it acts like a prism in that you get a refractive angle designed here to be at about 20 degrees. And for this particular application, you again have these polarizers in opposite directions because it does switch the polarization of your field. But in this particular application, you have an efficiency of about 60%. So pretty good. Okay. So one can actually move on from these passive elements to ones that can be actively controlled. So again, we have our little antenna, our split ring resonator. And we, again, model it as an RLC circuit. So the resistance is basically the loss in the metamaterial. The inductance is the inductance of the loop. And the capacitance is caused by the gap here. And if you can actively alternate these, and that will change the resonance frequency. So you can do this dynamically, either tuning through optical excitation, tuning through voltage. You can also tune by tuning the substrate temperature, although I'm not going to show you an example of that. So here we show an example where what we're doing is we're changing the geometry of the capacitance. The way we're doing this is we've got a set of a resonator array on sapphire with a gold structure that's permanent. And then we've got these two little silicon arms that come out. If we photoexcite them, then we make, if they're not photoexcited, the geometry is like this. We photoexcite them, and we've got a change in the capacitance. And so that's what we do, is we photoexcite them. And if we change the capacitance, since the frequency is 1 over omega equals 1 over LC, you get actually, as you excite it, so this is the resonance at 0 excitation, no excitation. As you increase the excitation, so you keep increasing the excitation, you actually can change the resonance frequency. And this is actually almost like a phase transition, because you have one well-defined resonance frequency, and upon photoexcitation, you have a change in resonance frequency. So optical excitation is nice, but actually being able to change a resonance or change the transmission through a voltage, so it's more like an electronic circuit, is even more important. And so again, you've got your split ring resonator. It's on a semiconductor, which at zero bias is conducting. So actually, the gap is not as active. You don't have a very large resonance. You do have some resonance. As you increase the voltage, you deplete the charge carriers. So this becomes more like an insulator, okay? And since this is electronic, you can modulate, you can make this into a temporal modulator. You can also pattern something and make this into a spatial modulator. One could also photoexcite this and make a modulator that's photoexcited. So this was our initial demonstration. So you can see at 0 volts, that's the blue curve here. The transmission is pretty high. As you increase the voltage, the transmission becomes less and less. So you've got the basis of a modulator. So if you do this at a certain frequency, you can get a modulator at a certain frequency. You can also pattern a device with different pixels and address them independently so that you have a spatial light modulator. So this is kind of a summary of what I've talked about so far. If you've got these few layer metamaterials, you can achieve many terahertz and or optical functionalities from spatial light modulators and terahertz modulators with that's basically a single metasurface. Bilayer metasurfaces, you can get perfect absorbers, AR coatings and filters. You can also get this polarization conversion, either linear to a different linear polarization or linear to circular polarization. And then you can demonstrate, and then you can implement flat optics where I've talked about prisms. You can also, by tailoring the phase radially, you can get lenses. So, and these all of these in the terahertz, but by changing the dimensions, you can go up to optical frequencies. Okay, so I've talked about manipulating terahertz light using metasurfaces. Now I'm going to talk about generating terahertz radiation using metasurfaces. In particular, what I'm going to talk about is what we've done with hybrid graphene nanoplasmonic metasurfaces. So this is the structure that I'm going to discuss. It's basically, you've got a quartz or a fusilica substrate. You put a monolayer of graphene, and then you get these you deposit these nanoplasmonic antennas that absorb at the wavelength you're going to excite. Okay, and then you can measure the current, which will be a directional current. This is vectorial, so depending on how you arrange these, you can get vector currents, you can get vector terahertz beams. You definitely get ultra-fast terahertz radiation if you excite it with an optical pulse, because you get a dJdt on a picosecond time scale. You can design these to tune the photocurrent by tuning the photocurrent direction by different kinds of patterning, and that will enable the rotation of terahertz polarization. And this is basically a phenomena that's enabled through symmetry breaking. Okay, so just to describe the basic concept one more time. You've got a quartz substrate, a graphene monolayer. It doesn't really have to be graphene. That's what we've used, but you could use 2D materials. You could use other conducting materials. It does have to be conducting. If you, okay, you can excite it with CW light, and then you get a directional current. And if you excite it with a short pulse, because of the dJdt, you get directional emission or directional terahertz emission. So in more detail, oh yeah, and if you pattern your structures, you can get vectorial currents, and when you excite it with terahertz, you can get vectorial terahertz emission. So I'm going to talk about both of these kinds of directions. So in terms of the graphene layer that we used, it was nothing special. We bought it from a commercial vendor. It was, had defects. We transferred it to the quartz substrate. P-type graphene was used. That's what we had. And it had a carrier mobility of 1,500 centimeters per volt second. The nano antennas that we designed, we use commercial software, and this is what we use for a lot of our designing our metamaterials. We design it such that there is this is a simulation, an absorption around 800 nanometers, which is the wavelength of our excitation pulse. And you can see the E field you design has a hot spot along the symmetry axis at the small end. And that is what produces your directional current. So you can actually fabricate these using E-beam lithography. So this shows you a micrograph of the plasmonic structure and of the arrays. And then you can actually measure with these structures the what's happening? Why isn't this? Something is coming up. I don't know what's coming up. Okay. You can actually, I hope not. Something came up and then what is this? Do I just see something came up on her computer, I think. Let me just see if maybe it works now.
Back in now.
Yeah. Okay. All right. So you can then measure the transmission, and it matches the simulation reasonably well. So you've got what you want. Okay. So then one can measure the photocurrent and the terahertz emission to basically characterize the metasurface response both to excitation wavelength and polarization tunings. So if we first look at polarization tuning, where this angle theta is with respect to the symmetry axis, that's one measurement we can make. We can measure the photocurrent. We can also measure the terahertz transmission. We can also measure the emission and the photocurrent as a function of wavelength tuning. So tuning, say, through the resonance that I showed you on the previous slide. Okay, so to do that, we use terahertz emission spectroscopy. So we have our ultra short pulse. We have our metasurface. We put it into a zinc telluride optoelectronic crystal in order to measure the terahertz waveform by scanning a delay line. So we scan the pulse across the terahertz. We scan the optical pulse across the terahertz waveform, and we get a waveform out. In order to compare and understand the emission strength and the bandwidth, we actually compare the emission from our metasurface to the emission from a standard 1 millimeter zinc telluride crystal, which is characteristic or the kind of terahertz emitter that one uses in a number of applications. Okay, so if we look at the photocurrent emission over a fairly large range of optical fluences, we see it's more or less linear. It becomes nonlinear at higher fluences. The terahertz emission tracks pretty well with the photocurrent signal, as you would expect. And you can get to too high a fluence, and you damage your structure, and then you don't get anything out. And that's kind of what's happening as we approach that fluence. The linear regime rolls off. So the metasurface response, it exhibits this resonance enhancement. So if you look at the photocurrent, it overlaps with the absorption of the optical wavelengths, the optical excitation wavelengths. And you can also see that the terahertz emission, which is in red, also tracks the resonance fairly well. If you look at the polarization dependence, you can see that as you tune away from the symmetry axis, you get this dependence, which is actually a cosine squared dependence. However, the terahertz for a structure where you have all of the plasmonic structures aligned, the terahertz emission will always be in the same direction. It won't change. It's just the intensity that changes as you change the polarization of the excitation pulse. If you look at the terahertz emission efficiency, this is a terahertz waveform from the metasurface. And you can also look at the bandwidth. The bandwidth is actually limited to 3 terahertz from our detection crystal. If we compare this to the zinc telluride crystal, it's comparable. So this is a pretty efficient emitter, both in terms of the efficiency and in terms of the bandwidth. So the resonance frequency can actually be tuned by tuning the size of the structure. Okay, so this particular structure, and I'll show you in a little more detail, is optimized for absorption around 800 nanometers. We also did some experiments at 1.5 microns at the telecom wavelength. And again, you can see that it tracks what one would expect from the design of the emitter. You can actually see here the terahertz waveform that you get out. I had previously shown you what you get out at the 800 nanometer structure, which is shown here, and you can actually see how big it is. For this larger structure at 1.5 terahertz, you still get comparable to zinc telluride in terms of emission, maybe not quite as optimized. So you can also look at the excitation wavelength dependence in more detail, and you see that you'll see that the plasmonic resonance dramatically enhances the terahertz emission. So that's what you get at 800. So you can see that the peak emission is around is at 800 as it was designed. And if you look at our 1.5 micron emitter, you can also see that the resonance enhances the terahertz emission. Okay, one final thing before we go into a little more complex discussion is that the graphene monolayer really is essential, or some kind of conducting layer is essential in the terahertz emission and in the directional photocurrents. So this is what you get with a graphene layer. And if you plasma etch the graphene layer off, you see that the terahertz emission goes from, the absorption stays the same. So you're still exciting the plasmonic resonators, but there's no current. So there's no terahertz emission. Okay. So as I said earlier, you can spatially pattern these resonator arrays or these plasmonic arrays so that you get vectorial currents. So this is an array that's been patterned so that you get radial currents, both currents and terahertz emission. And this one is patterned so you get azimuthal currents and terahertz emission. In terms of the terahertz emission, we collaborated with some folks at Menlo Systems who have a capability, a hyperspectral terahertz imaging capability, where you input circularly polarized light, ultra fast, and this was around 780 nanometers. And then you scan across the terahertz beam and measure both the X and Y components so that you can characterize this vector terahertz emission. And so for the radial beam, you basically get these measured Hermite Gaussian modes, which correspond to a radial vector terahertz beam that looks like this. And the magnitude, as it gets lighter, the magnitude is going away. But you do see a vector-like emission. The same thing for the radial beam. Again, the measured modes in the X and the Y direction of the E field. And then that corresponds, again, to a terahertz field that looks azimuthal in character. Okay, so you can go even further in terms of what you can design. And actually, I'm going to show you a few examples, but there are a lot more things you can do. So if you have a symmetry that, if you have a surface with a symmetry where you basically have an odd number, the symmetry is odd. So n equals 1, which we've shown you, n equals 3, n equals 5, etc. Anything above 1, you can actually use that to control the polarization while keeping control the polarization via the input polarization while keeping the output constant. And so what we did to demonstrate this was design and fabricate a Kagami metasurface, which is shown here. And as you change the electric field, which is, the electric field is the black, the excitation field is black in these figures, and the direction of the current is blue. As you rotate the input polarization, you rotate the direction of the current. And the formulas down here are for the X component and the Y component of the directional current, where theta I varies, goes from 0, 2 pi, 4 pi over 3, 2 pi over 3 and 4 pi over 3, 120 and 240 degrees. So as you do that, you can actually look at the amplitude of the terahertz signal as you rotate the input polarization, and it's basically constant, as you can see. But the polarization rotates as you rotate the input polarization. So you really are able to directly control both the photocurrent and the terahertz emission polarization, the direction of the photocurrent and the polarization of the terahertz emission by changing the incident light polarization. And you can actually, so this particular revelation inspired us to make kind of these structures which are a little bit different, but the structure itself has the symmetry. So you can actually both control the photocurrent direction and the terahertz emission, again, just by the excitation polarization, using this much simpler plasmonic array. And finally, you can design an array like this, where you have a structure that's basically circularly rotating, and this enables you to, by rotating the structure, because this has to be excited by circularly polarized light. By rotating the structure, you can actually, by rotating the polarization of the incident light, you can rotate, you can convert from an azimuthal in red emission and to a radial emission in blue. So there are a lot of different things you can do. You can actually even put plasmonic resonators with different dimensions, so you can excite the same metasurface at different wavelengths. There are a number of things you can do to make a more flexible capability to emit terahertz radiation. So in summary of this part, I think we've demonstrated this universal phenomena of directional current and terahertz emission that really comes about by symmetry breaking, by these structures that have broken the symmetry in the material. The underlying material here we showed was graphene, but you can actually use other kinds of materials as well. But they have to be able to, there has to be a way you can excite a current. Different mechanisms depend on for this phenomena depend on the interaction between the plasmonic structure and the underlying material. In the case of, we believe in the case of this graphene structure, we are seeing a photothermoelectric mechanism, but there are multiple mechanisms such as photoinjection and photovoltaic that could be possibly accessed. And there are a number of applications for this kind of a structure in terms of ultrafast sources, vector beams. You can imagine doing some kind of inverse to develop photodetectors. This is a way, I believe, because you're producing directional currents, of controlling the properties of the underlying material. Nanomagnetism and spintronics are also possible, again, by a different design of these resonators. So with that, I want to acknowledge the collaborators here. There are a lot of people that have contributed to this work. In particular, this work was led by Haotong Chang, who's a scientist at the Center for Integrated Nanotechnologies. And in fact, this work was done at the Center for Integrated Nanotechnologies, and I'll tell you a little bit about that in the next slide. In particular, the work on our vectorial hybrid nanoplasmonic terahertz generation was performed by a very talented postdoc, Jake Patin, who is now unfortunately, in Nugetics group at MIT. So this was supported both by Sint and by LDRD. And so my final slide is just an advertisement or information on the Center for Integrated Nanotechnologies. This is an Office of Science user facility, basically dedicated to nanomaterials research. And it is a place where you can access fabrication, characterization, and theory through user proposals. There are two user proposal calls a year. This is pretty simple. It's a 2-page proposal. That is for research that is open. If you have proprietary research, which is probably not the case here, we're required to get full cost recovery. But the capabilities span in situ characterization and nanomechanics. This includes electron microscopy, nanophotonics and optical nanomaterials, which is the thrust that the metamaterials area lies in, soft biological and composite nanomaterials, and then quantum materials systems. So with that, I guess I'm open for questions, and thank you for your attention.